This is the final project presentation for Group 3 Fast Versatile Video Coding. The team members are Michael Romero, Cameron Veet, and Connor Veet. The original goal of the Fast Versatile Video Coding project was to speed up the encoding process of the VVC encoder. This is because the VVC encoder can compress higher definition video at the cost of processing time. As such, by increasing processing speed, the downsides of the VVC encoder compared to other encoders can be negated. The method by which the processing speed of the VVC encoder will be increased was originally by training a neural network to short-circuit cost analysis of possible options. This would greatly reduce processing time by sending the configuration file from an AI directly to the VVC encoder instead of having it be set by the person using the encoder. This neural network would be integrated with an already existing encoder implementation, the original VVC encoder.
In order to achieve the goal of increasing processing speed, further development is needed. Doing so requires us to break down the training pipeline and encoder integration into smaller tasks. Those tasks were extract data from existing encoding log files, design and train a neural network on prepared data, and integrate a neural network into pre-existing encoder solutions.
The current goal of the Fast Versatile Video Coding project is the same as the original goal, to speed up the encoding process of the VVC encoder. The method by which this is done, however, will be different, as instead of using a neural network to make the best configuration options, the neural network will replace one of the steps. To be specific, the neural network is created to replace the segmentation process of the normal VVC encoder. The deep video encoder functionally should be able to reduce complexity in order to increase processing speed without a quality decrease, should be able to predict computationally intensive modes in a video encoder, and should be able to analyze parts of the video and determine which coding modes are best to maintain quality. The deep video encoder shall be able to function through the terminal, shall be a downloadable plugin, shall be installable through the terminal and or through download, and shall be toggleable. Additionally, the deep video encoder shall have safe software development practices for safety concerns. Next up is the design diagram of the entire system. The diagram comprises of three main subsystem units. These units are the AI unit, the encoder connector unit, also known as the data ingress unit, and the toggle unit. All these units are run on a single operating system and are made up of processes that use basic message sharing techniques to communicate, such as shared memory or discrete message sharing operations. At the current point in time, they are not currently integrated onto a single operating system. The AI unit takes the video data and segments it. It then sends this segmented video to the data ingress unit. The data ingress unit then creates two-digit binaries based on the data from the AI unit and sends this to the toggle unit. The toggle unit then uses these binaries if it is active. If it is active, these binaries either tell to disable or enable binary and ternary splits for each macro block. It then encodes the video. If the toggle unit is inactive, then the VVC encoder runs as normal. The AI subsystem of the deep video encoder takes a sample video and separates it into its frames. Each of those frames is then put into the Detectron2 to create a mask of each frame with the objects classified. Each of those masked frames is put into the segmentation network to create each frame separated into blocks. Those segmented frames are then put back together to create a segmented video. However, this process is a lot more complicated as is described here. For one, after you segment the video into blocks, you need to put each frame back together by getting the upper left-hand corner of each block. Not only that, you have to check for errors in the process to make sure that when you put back together the segmented video, there will not be any problem.
The original design had us encoding a video and feeding the partition information into a learning algorithm to train a neural network. This required a log parser to be made to read the partition decisions of the VTM encoder and an AI platform such as TensorFlow to train a neural network.
Continuing onwards is the final design of the toggle subsystem. This subsystem uses a toggle variable to designate whether the normal or modified version of the VVC encoder is used. If toggle is set to on, then the VVC encoder reads a list of 2-digit binaries from the data ingress unit for each frame in order to disable or enable binary or ternary splits for each macro block in said frame. This is done by setting the maximum size for binary and ternary splits to 0 if they are disabled or to 32 if they are enabled. It should also be noted that the config file shown in this diagram refers to the typedef.h file, in which the definitions are set. The deep video encoder was previously planned to be compatible with both Linux and Windows computers, and a supercluster was provided by the problem sponsor to train the neural network. Additionally, the project was supposed to consist of various software subsystems mentioned in the project design, with the subsystems working together to create a functioning program that takes video data from the encoder, determines which mode should be used to best encode the video, and sends that data to the encoder so that the video can be encoded efficiently. Finally, the languages required were supposed to be Python and C++. However, as it turns out, this was not fully the case.
The hardware we need for this application is any Windows or Linux compatible computer. The project consists of various software subsystems mentioned in the project design. These subsystems were unable to be integrated with each other at this time. The subsystems would have worked together to make a functioning program that takes video data from the encoder, uses the Detectron-2 alongside a neural network to segment the video, run the segmented videos for a parser to find the types of splits used for each macro block, and then segments the videos in the VVC encoder using a binary output from the parser to decide which splits to be used. The required languages are Python and C++.
The AI subsystem of the deep video encoder is different from our original intention in that it uses a neural network to separate the frames of a video instead of taking a video and finding which way to separate it would be best. By that, I mean that it actually does the segmentation instead of finding the best way to encode it.
It was decided mid-project that we would use the Detectron-2 platform to generate the segmentation information so the need to find a learning algorithm and train a neural network would be alleviated. As such, the log parser to retrieve the encoding information from a log was still developed in a Python script and output in text log to be used by the encoder. The log parser makes heavy use of regular expressions to retrieve attribute information about a block and nested dictionaries to index a block by frame and coordinates.
Next up is the final implementation of the toggle subsystem. As can be seen in the diagram, this matches the final design of the toggle subsystem as well and varies greatly from the initial design. Instead of taking results from the AI unit to use as a config file like in the original design, it uses a list of 2-digit binaries from the data ingress subsystem to either disable or enable binary and ternary splits by changing their max size for each macro block in a frame.
Because of the inability to run the AI subsystem locally, all of the subsystems were tested independently of each other instead of as one large unit. This was not an issue, however, as each subsystem was tested based on the output of another subsystem. The AI subsystem had built-in error checks in the code, and the code was modified to pass these checks, giving the correct output. The data ingress subsystem had errors that were thrown if the parser achieved an undesired result, including the inability to match the text to an attribute or being unable to associate a block with a partition based on splitting logic. The code was modified as needed so the errors were not thrown in the process of parsing a log. The toggle subsystem ran the VVC encoder with the toggle variables both on and off. Encoding times and block sizes were compared to one another. When toggled off, the VVC encoder ran as normal. When toggled on, the VVC encoder ran using binary output of the parser to disable certain types of splits. The final plan ended up vastly different from the original plan. A majority of the tasks were divided into subsections over the course of a few weeks. The tasks reached towards a different end goal. Instead of creating an AI to make configuration file recommendations, the AI segmented the video in place of the VVC encoder. The goals that were completed was a toggle subsystem that was completed as far as possible as the current development state. It is able to hasten the segmenting process by disabling specific splits. The AI subsystem can completely segment a video much faster than the original VVC encoder. The data ingress subsystem is able to make segmentation data and turn it into binary information used in the toggle subsystem. The goals not completed was the subsystems were not integrated due to difficulties running the AI subsystem locally.
Lastly is the lessons learned, outcomes, and possible future research. Throughout the course of the project, a multitude of lessons have been learned. These include the importance of properly distributing the workload, the need to properly understand the path to the end goal at the start, the necessity of understanding the topic at hand in detail in order to gain a better grasp on what exactly needs to be done in order to accomplish certain tasks, the importance of having good communication about issues with both teammates and problem sponsors, as well as the need for proper documentation of the systems in order to use them correctly, especially when the system is not widely distributed. Additionally, despite the inability to integrate the subsystems together, by running each subsystem separately and sending the output of each to its required subsystem, the time spent encoding a video using the modified process was less than the original VVC encoder. In addition to a desired outcome for the fast versatile video coding project, the possible future research has a lot of potential. To be specific, it is possible to greatly improve the processing speed over the current stage of the fast versatile video coding project by integrating the subsystems together and then removing the data ingress subsystem. This would cause the AI and toggle units to directly connect to each other for a much better processing speed. This is the AI subsystem for the deep video encoder, and I would run it for you, but that takes 13 minutes, so I'll just explain it. So these three functions are used to grab all the libraries necessary to run a segmenter, and the rest of it is a bunch of functions that actually segment the video. This is like the overview you put in the video, and it actually does all the segmenting. This function gets the frames from the video, as you can see here, and then each frame is done one by one. This function gets the mask of the current frame, and this function takes that mask and actually does the separation process. This is the first part of the separation process, which separates each frame into a basic 128 by 128 blocks, or smaller if it's not divisible by 128 by 128. This function separates those 128 by 128 blocks into their actual, block derivatives. And this function down here finds the upper left-hand corner of those blocks. This function down here gets the version of the blocks in the regular frame, not the mass version. And this one put that information into the text file to recreate the segmented video. And these three things down here actually, allow you to run the video. This gets you through the video. This actually puts into the segmenter, and this allows you to get to the result. Anyways, so this was not able to be implemented with the other two parts because it's more accurate than the actual VVC in that it isn't limited to where it can place its blocks. Although the block size is still limited, so it's not suitable to connect to the VVC encoder because its blocks might be in positions that the VVC encoder won't accept.
Okay, this is the script for getting the segmentation information from the pre-recorded log. So you would record a video in the VTM software unmodified, and it will give you a log file of the encoding process. So you would, this is just command line thing so far, so you just do log parser.py and preface that with Python, which is in the file path. And you also, because it's not meant for command line use, it is hard coded the file that's being rendered and hard coding the output file. But that could be easily modified. So right now I removed all the print statements, so it's going to be very plain, the output on the command line. And the resulting log file is going to be something like this, where it's two-digit numbers in an array. There's 5 frames in the coded video that we did, so there's only 5 rows. And as you can see in the first row, every macro block in that frame uses both binary, which is the first digit, and ternary splits, which is the second digit. And you can see in the subsequent frames, there's a mix of not using any, using one, and using both.
Next up, we have the last unit in the fast versatile video coding project, the toggle unit. The toggle unit starts in the typedef.h file, in which the enable FVC variable is defined. This variable determines if the toggle unit is on or off, with a 1 being on and a 0 being off. This mainly affects the enc slice.cbp file, in which if the toggle unit's on, then it grabs a list of 2-digit binaries for each current frame. As you can see here, each frame is a different text file. Then, inside this loop, for every single macro block in the frame, it ends up using the enable FVC variable again, where if it's on, it says fast VVC encoder enabled, and then changes the maximum size for binary and ternary splits based on the current 2-digit binary. This either disables them or enables them. It grabs the current 2-digit binary for the macro block, and then if the binary is 00, then both of them are disabled and set to 0. If it's 01, then ternary is enabled and set to 32, but binary is set to 0 and it's disabled. If it's 10, then binary is enabled and set to 32, and ternary is 0 and disabled. And if the binary is 11, then both of them have a maximum size of 32 and are both enabled. If any other value is entered that is not a binary value, then you get a valid entry. After that, compressed CTU is called, which basically divides the macro block into smaller blocks. As you can see here are the frame 0 and frame 1. Additionally, you can see the output blocks for both when the toggle unit is enabled and when it's disabled, which have the same output. Lastly, you can see the times right here. This is when the toggle unit is enabled, and as you can see, it's just under 30 minutes for 5 frames. And this is when the toggle unit is disabled, and as you can see, it's just under 50 minutes. Though this excessive time may be because of a slow computer lag or something. But as you can see, when toggle unit is enabled, it is faster.